Hi there, this is a little bonus video on electric circuits and hints, in addition to paper 1 revision for the exam. I thought I'd do this as a recording and upload it before time, and then we can do the live session on the Wednesday night before the exam. Now, circuits are weird, so I thought this merits doing a little standalone video. I'm going to explain a few things about circuits to you, perhaps my way of explaining circuits. And the thing is, if you know them by now, great. Skip this video, don't watch it. If you're still struggling with circuits, something might come up today that might just click with you that will help you in the exam to do the P2, the electricity part. So, let me start by saying, if your science teacher claims that their version of explaining circuits is correct, then they are talking rubbish. Unless they're going to be using Maxwell's equations, everything is going to be a compromise. Okay, everything will be a model. There's no one model better than anything else. All we're really doing is we're trying to figure out if we build a circuit and design it, and we want to get voltages and currents and resistances and all these values out, what goes on in the circuit is a bit of a mystery. Okay, models that we have are simply just ways to try and predict what these numbers will be, and we can do that fairly well with a simple model. We have equations, we have a way to visualize circuits. Is it genuinely what's happening in a circuit? No, because these equations are what really determines what goes on, but we have to start somewhere. And we're going to start today with my model. Okay, now before we continue, we've got a bunch of symbols here. I kind of made a bit of a mess of the LED. You've got to know these symbols. They attach to you draw circuit diagrams with them in straight lines. They've all got a particular function. One of my pet hates is the fact that switches are drawn either as open or closed. That's like an architect drawing a house. One version with all the doors open and another version with all the doors closed. It's a door, it's designed to open. It's a switch, it's designed to be pressed. Okay, so please don't worry about memorizing switches closed and switches open. They have a job to do. They complete the circuit or they disconnect the circuit. So let's, I'm assuming you know all this stuff, so let's move on to the model. Okay, now I established this over the course of my teaching career. I've kind of settled on this as being my way to explain circuits. We have a food depot, we have roads that connect up supermarkets, and we have lorries. Now these little rectangles are lorries. Now I want you to notice the only thing that moves in the whole model, are the lorries. Now I prefer this model to perhaps the water and the pipes model, simply because water flowing is a reasonable model, but I like the fact that there are physically things moving along the circuit. And I know before any of the pedantic teachers say, well, actually electrons don't move that quickly, again, we're not using Maxwell's equations. This is a model to help explain the numbers that we see in real circuits. So let's dive in. The lorries in my model are the only things that move, and they are electrons. Now, electrons are tiny, they have a tiny charge, and so to count the number of electrons, I think we have something like 6 million billion electrons in what's called a coulomb of charge. So we're going to call this charge. The things that move in a circuit is the charge, and those are many, many, many electrons. So 1 coulomb of charge will be a big bunch of electrons. 2 coulombs will be twice that many. The food depot, which is the source of the food and the energy, is the battery or the cell. Okay, so we have a cell, we have a battery. Hang on, Mr. Greer, where does power stations and where does plugs fit into things? I can plug in my laptop or my phone charger. That's not a battery. Yes, you're tapping into energy via the national grid to a power station. So the power station is a source of energy. You're just accessing it from a big distance away using the mains on the national grid. The food itself, the things that is carried onto the back of the lorries, that's going to be our energy. And the supermarkets are where we drop off the foods, and in a circuit those are where we drop off the energy, and those are called output devices. output devices, and those could be things like motors, bulbs, LEDs, resistors, heaters, anything that we can interact with. Now, I'm going to skip these two for a second and jump down to the roads. The roads themselves connect up the cell of the battery to the output devices. The lorries move along the roads, and these are called wires. Now, we're going to keep it fairly simple just now in terms of our definitions. I know this is an approximation. Now, I'm going to choose a little bit of colour scheme here. I'm going to choose, let's choose red for the foot per lorry. Now, the foot per lorry is energy per charge. Now, we can write that as E over Q. In actual fact, we're going to start to label some of this stuff up. So the lorries themselves, the charge is actually get the symbol Q. The food, which is energy, has the symbol E. This is measured in coulombs. This is measured in joules. Now, my pupils often mock me because I say J for joules. In Scotland, we say GHI, J, KLM. But in England, apparently, it's J. Okay, that's why I failed in my career as a DJ in England. The foot per lorry is the joules per coulomb, or the N or E over Q, and this is called potential difference. So potential difference, it's sometimes referred to as voltage. In fact, I may even slip into that bad habit today. So it's called voltage or potential difference, and it's the energy over the charge, or joules per coulomb. So volts is joules per coulomb. How much food is in the back of the lorry? And for the lorries per second, well, time is time is a measure measured in seconds, so that's going to be T. And the lorries per second, that's the charge per second, so it's Q over T, and that is going to be our current. So our electric current is our number of lorries passing by every second. Okay, Q over T. Now, those equations will be given to you in the exam. Again, it's good to know where they come from. They're literally the definitions for potential difference and current. A bit of rearrangement there. Now, let's go to the model itself. The lorries that leave the food depot, we say, are full. The lorries that enter are empty. So all of my energy from the food depot, all the food is used up around the circuit by the various supermarkets. And the lorries are full here, they're full here, they're still full, still full. Eventually they drop off some foods, and we can say here that they are half full or half empty, depends on your output. Now, how can we measure this? How can I measure what's been dropped off at the supermarket? I need two people. I need somebody standing there, and this person says, the lorries are full. And this person here says, okay, I'm seeing the lorries half full. And between them, they agree that the lorries that were full here and now they're half full there, they must have lost half the food in the supermarket. And so to indicate the potential difference that is dropped, or the energy used per coulomb in an output device, we need two people or two positions, the before and the after. And here, if we have another person up here, that person say, the lorries are empty. And between this person and someone standing there, they'll say, okay, they've lost half of the energy or half the potential difference in the supermarket, and they go in empty. So voltage or potential difference has to be measured between 2 points. That's a voltmeter. The current relies on somebody standing at the side of the road, or perhaps even in the road, but that's dangerous, and they're going to have a stop clock. And they are going to simply measure how many lorries pass by them every second. If it's 5 lorries per second or 5 charges per second, that'll be 5 amps. If it's 10 lorries per second, 10 amps. But remember, in real circuits, you might get small values, so there could be 0.5, 0.2, 10 milliamps. So it's going to be 0.01 lorries per second. This is where the model you have to be a little bit flexible. So to measure the current, you stand next to the road and count the lorries passing by each second. To measure the voltage, you have to have 2 people, 2 positions, comparing the before and the after. And in any circuit, the lorries leave the circuit full and go back into the food depot empty. All the voltage is used, all the energy is used. Now, if we had different size supermarkets, say here, then if I was to draw, just going to indicate what's in the back of the trailers for these, then I used red for potential difference. Let's keep it red. So remember, lorries leave the food depot full. So this would be full up. Have I lost anything? Have I used up any potential difference here? Any voltage? No. So it's still going to be full here. I know that they must enter empty, so this one's fine. So we have a decision to make. How much do I colour in for this lorry? Well, this hypermarket is much bigger than the mini market, so this will use up much more of the energy than this one. So I need to draw a tiny amount, or maybe a smaller amount of food in the lorry. So this has used up most of the energy. The remainder will be used in this supermarket, and then they go in empty. And again, I would have some kind of a voltmeter to measure the difference. Okay, to measure how much voltage is lost in this or used up in that hypermarket. Now, the current is determined by the lorries. Now, this is where the model, you have to sort of think of the model. The speed of the lorries as they drive around is constant. Okay, and if we had a big 3-lane motorway, then we could perhaps have more lorries per second, so that would be a higher current. If we had, now say imagine we've got some roadworks. We've got some roadworks up here, and this bit of the road is blocked, so the lorries have to slow down and go round the roadworks and go back in. Because this lorry's slowing down, the whole network, the whole circuit slows down, so the current reduces. Because my resistance has gone up somewhere in the circuit, the whole current has to decrease. Okay, we'll come back to that later on. So how do we do this then in real circuits? Okay, let's switch up and let's have a look at using this model in real circuits. Let's begin with current in a circuit. We're going to use an ammeter. Ammeters sit in the wires, and the rule is the current that leaves the battery is the same that enters. So I've got blue for current. So if 2 amps or 2 lorries per second leaves the cell of the battery, it must be the same that enters. Doesn't matter what happens down here. If 2 leaves, 2 must enter. The current number of lorries per second goes along, still 2. I've not done anything, still 2 amps there. We get to a junction. Now here's the key to it. Some of the lorries go down this road. The remainder of the lorries will go down this road. And I've figured out here, because I wrote it, that we have 1.5 amps that goes down this road. So that means this must be 1.5 amps. And then this junction, the lorries that drove down this road, recombine with the lorries that drove down this road, or this branch of the network. So this must be 2 taken with 1.5, which is 0.5 amps. And then we have the 2 amps, which goes along and back into the battery. So that's how current works. Now, I've not said anything about series or parallel, because I don't want at this stage. I want to just look at the lorries in a circuit. When the current gets to a junction, the current splits up. Some lorries go down one branch, some go down another branch. Now let's look at potential difference, which I'm going to do in red. So now we've got the voltage potential difference in a circuit, and here the voltmeter, I've got my two positions. I've got one there, one there. That's the two people that are going to compare the before and after. Now, we've got a cell, we've got 12 volts. So this is the energy that every coulomb of charge will have developed in the cell, the chemical reaction. Now here's what I want to do. I want to just go through how we label up a diagram. Again, I don't care if it's parallel or series just now. I know that lorries leave the depot, leave the battery full. So they're going to leave here with 12 volts in their trailer. They're going to enter with 0. Now we have to think about, have my lorries used anything up? No. So here, at this point, it will still be 12 volts. Here, it will still be 0 volts. Let's continue down here. The lorries are going to drive down this road. They still get 12 volts, still get full trailers. They get to this point, they're still full. Now here's the tricky bit here. The lorries themselves split up. Some lorries go down this road, some go down this road. But remember, they still get full trailers. So the lorries that drive down this road take the 12 volts. The lorries that drive down this road still take the 12 volts. And so we have to look at individual branches now, where both lorries start with 12, or both branches, sorry, the lorries start with 12 and lose some voltages or potential difference. But there's a catch over here. They have to come to this point with 0 volts in the trailer, which means they must have started beforehand with 2, because we drop off the remainder 2 volts of energy to the supermarket and we end up with empty trailers. So there must be 2 there, and again, like over here, the lorries arrive here with 2 volts. Whether they come down this road or the bottom road, they arrive with 2 volts. Now let's look at each branch individually. 12 volts down to 2 volts, that's got to drop off 10 volts of energy. 2 is dropped off there, 6 is dropped off there, this one must be 2. That adds up to the 10. This branch, I've got 12 to begin with, I lose 7, I want to get to 2, so I've got to have, that's got to be 3. The lorries start with 12, they go down to 5, they lose 3 to get down to 2. So that's the potential difference in a circuit. What about if you have a combination of both? So let's do one of those, and yeah, let's do this one. I'm going to put all these files online if you want a bit of practice, just to do it for yourself. So we've got to deal with, we've got lots of ammeters, lots of voltmeters in the circuit. Let's do the set of one for, let's do the current first of all, which is the ammeters which sit in the wire. If it's a voltmeter, it's going to have these legs which attach before and after. I know that 4 amps or 4 lorries per second enters the depot, which means we must have had the same that leaves on the other side. That's going to be 4 amps. Again, we don't look at the 3 here, we just think 4 amps, 4 lorries per second drives through this one, drops them off at the supermarket, keeps going. 4 amps arrives at this junction. 3 of those lorries per second go down this road, which means there must be 1 amp left over for the bottom branch. And that's my current solved. Let's solve the circuit for voltage or potential difference. The rule is the lorries leave full, they enter empty. So they leave full, they enter empty, and then let's expand out. The lorries drive along with full trailers. Remember, that doesn't use any voltage, that's just somebody standing in the road with a stop clock. The lorries are full, they go into here, they're going to have 10 volts. Over here, nothing is, again, that's a person with a stop clock counting lorries, so it's still the trailers are empty. The trailers go here, they're empty, they get to this point, and there must have been 2 volts here because they have to have dropped off that final 2 volts of energy in this supermarket, this resistor. And remember, because the lorries arrive here with 2 volts from both branches, it's 2 volts, 2 volts. Over here, 10 volts on the back of the trailer comes here. This supermarket demands 3 volts, so they leave this one with 7. And again, the lorries drive down here with 7, and the remainder drive down this road again with 7. And so we've got 7 down to 2 in the bottom branch. That's going to be 5 volts lost. 3 volts there, must be 2 volts there. 7 down to 2 here, that's 2 plus 1 is 3, plus 2 volts is my 5. So there we go. So we've just done not just a series circuit, not just a parallel circuit, we've done a mixed circuit. Okay, and we'll do one more, and then let's put some Ohm's law numbers onto this. This circuit's quite cool, because there's a catch to this one, which is I've not given you the battery or the cell. So we have to use the idea of full lorries and empty lorries. There's nothing down the sides, so really all the energy is lost between each side of the branches. Now let's do the current first of all, which is the blue. What enters must leave. So 3 amps enters, 3 amps must leave. 3 amps, remember, is the number of lorries per second, and that's going to be 3 amps till I get to now there's a junction. 0.5 of the lorries go down this road, the remainder go down here. If I could put an ammeter in this position, it would say 2.5. It gets to this branch, and then I don't know what that is, but I know that the bottom branch is 1.5, so actually these 3 added together will add up to 3. So 0.5 and 1.5 is 2, the remainder is 1 amp. Solved it. Let's do the voltages, the potential difference. This is trickier because I don't have this information here. But what I do know is that the lorries enter empty. So I know it's going to be 0 volts, and there's nothing over here using up any energy, so all the lorries that arrive at this point will all be empty. Is it a clue as to what the value is over here? Not in this branch, not in this branch, but this branch is the key. Because I know that both supermarkets in this branch use up 4, which means that the lorries that drive down this road, to end up at 0, they must have begun with 8. So that's going to be 8 volts. Now it just so happens, all the lorries that arrive at this point have 8 volts, which means everything connected to this side of the circuit, because there's no resistors over here, are all going to be 8 volts. If I can write clear, it'd be better. 8 volts, 8 volts. So 8, 8, 8, 8. Which means if somebody's standing there and says, oh, hang on, the lorries are empty, and someone's there saying, oh, the lorries have 8 volts, then between them they decide that in the food depot or the battery, it develops, hang on, that's 8's not a nice number to write with the big felt tip pen. So 8 volts is developed in the battery or the cell, and that 8 volts is delivered to the circuit, and these branches use up 8 volts separately. So this branch here, we get 8 down to 0, so we get 3 and 1, we're left with 4 volts. And down here we'll get 8 down to 0, we've got 2 there, so we must lose 6 volts in this one. And there we've solved it for a mixed parallel circuit with series branches. So let's just have a little recap we've done. We've actually analysed some pretty complicated circuits, probably way beyond what you'd be expected to do in the exam on Wednesday, or any future exams if you're watching this not in May 2025. But we've just analysed circuits using lorries and supermarkets. We can solve pretty much any circuit with resistors because we're sticking to the model rather than learning independent series rules and independent parallel rules. Okay, yes, we've just shown that in a parallel circuit the voltages are the same across every branch, but we've shown it by using our lorries and a supermarket's model. We've also shown that in a series circuit the voltages divide up between components in series, but we've done it using our model. We've shown that in parallel circuits the current splits up across parallel branches, but we've also shown that the current that leaves a battery must enter. So in a series circuit the current is the same everywhere. In branches it splits up, in series they are the same everywhere. For example, down a particular branch they're all going to be 0.5 down here. So we've done the rules for series and parallel, we just haven't specified that's what they are. Now let's do something a bit more examinable, which you'll have to face on in the exam. Let's have a look at this here. Now let's use, I'm going to get another bit of paper first, and you're going to have to use Ohm's law. So again, you cannot escape Ohm's law in electric circuits, and it's simply the equation potential difference is equal to current times resistance. You have to rearrange this and use it in various forms, so voltage divided by resistance, and the last one, the resistance is, again I call it the voltage, potential difference divided by current. Now, to say which one comes first is wrong. You know, I always think about it as you've got voltage, you've got current, and you've got resistance. They all inform each other. Okay, so you can't ever discuss one without using the other two. There isn't any one that came first. You can set the values in a circuit. We can choose the resistance in the circuit. We can choose the input voltage. The current then follows from that. But you can't treat it as one comes first, the next one comes second. They all exist simultaneously, and they all relate to each other. So let's use Ohm's law and let's apply it to real circuits. So let's go to this one. Now let's use a combination of the model with the lorries, and let's use Ohm's law to tackle the questions. And we have to fill out the various voltmeters and ammeters. Oh, here's an easy one. Because I'm given the ammeter for the current that leaves the cell, I know that what must enter is the same, so 1.5 amps. I also know that because there's no branches in this circuit, it's the same value everywhere. So down here it's going to be 1.5. I'm just going to omit the units now because I'm running out, the pen's quite thick. And I get along here's 1.5. Because if anyone was to stand in the road counting the lorries per second, they would all count the same number of lorries per second. Remember, in a series circuit like this, the current's the same everywhere. Let's tackle the voltages. We know that what leaves the battery is going to be full, so 18. What enters must be empty, so 0. It's going to be 0 over here. It's going to be 18 over here. Now we have, but I don't know how much I lose. I know that the current is 1.5 amps. I know the resistance is 2 ohms. But what's the value of the voltage? Well, we have to go back and use Ohm's law, which is voltage is equal to current times resistance. We're going to apply this to this one component. And so we have 1.5 amps times 2 ohms, and that gives us 3 volts. So the value in here is 3 volts, which means that the lorries lose 3 volts here and end up 18 take away 3, which is 15. So they arrive here with 15 volts. Let's do the same down there. Okay, this is a bigger resistance, but we use the same equation. And because the current's the same, it's going to be V is equal to I times R, which is 1.5 times 4, and that equals 6 volts. Actually, something to notice, in a series circuit, because the current is the same everywhere, if I double the resistance, then I must double the potential difference. So 3 volts for the 2 ohms, it must be 6 volts for the 4 ohms. And that goes in here. 15 volts in the lorries started over here. We lost 6, so we end up with 9. Now I could just write in the number here straight away. There's no other supermarket between this point and this point, so all the lorries must lose 9 volts. Job done. But let's just use Ohm's law to prove it. And so we've got voltage is equal to current 1.5 times the resistance of 6 ohms, and that equals indeed 9 volts. Done. I want to show you another circuit. I did this one earlier. Here again, I don't want to write it all out. I'm going to just talk you through this one. So here is another circuit. Now here we weren't given any of the values. We had to use Ohm's law for the whole circuit. Okay, so essentially what I did was, if you're standing here, standing there and you're looking around the whole circuit, how many ohms will you face in total? Well, you'll come to the 50, then you come to the 250, and then 150 and 150. Add them all together, you get 600 ohms. And so the rule is, for series circuits, the resistances add up. Just plain add them up. We'll do parallel shortly. Now, because I know the whole circuit resistance, I can apply Ohm's law to the whole circuit. 7.5 volts. And let me explain this one quickly, because what I can do here is this whole circuit can be replaced by, let's go to this bit, a same battery and so this can be replaced, the whole circuit can be replaced by the same cell or battery and one equivalent resistor. And I've said, okay, this resistor is 600 ohms because it is the combination of all four of these. And that gives me a simple circuit of a cell and a resistor. I use Ohm's law for the whole circuit. That's the equivalent resistance, 600. I get 0.0125 amps. And that goes into my ammeters here, here, and here. And then, as before, I apply Ohm's law locally to each individual branch, each individual component. And again, 0.625 volts here. This is 5 times bigger than this one, so it'll be 5 times the voltage. Indeed it is. Here's a curious one. These two are the same resistors, so they will have the same potential difference. If the supermarkets are identical, they'll have the same amount of foods. If the resistors are the same, they'll have the same voltage dropped across them. Okay, let's move on to power. Okay, you have to know about electrical power. Let me just get a bit of paper. And I'm not going to discuss the national grid in the moment. That's something that we can cover in there's a big revision session. Electrical power is essentially energy divided by time. That's the equation for electric power. That would be in the equation sheet. Okay, but we should know from our definitions. Let's go back to our definitions. That, if I can find it, I miss all my paper here. There we go. So my definition for energy, if I rearrange this equation there, so we've got energy is equal to, so energy is joules, charge is coulombs, potential difference is joules per coulomb, so the coulombs cancel, we end up with joules. So that is the equivalent for energy. And also we've got the definition for current, I equals Q over T. Let's rearrange that for Q. We end up with Q is equal to I times T. We can actually swap out the Q for IT. So we've got energy is equal to I TV. And then we can put this into this equation. So we have power is equal to, instead of E, we write I TV, all divided by T, and the T's cancel, and we're left with P is equal to I V. Sometimes it's written as VI, I don't know why. It's the same, it's just a product of current and voltage. So again, just in case, I can't remember, it's the same thing. Now we can use Ohm's law to be a little bit tricky, and we can actually come up with two other power equations, which are I squared R. Again, that's just swapping out the V. So voltage is current times resistance. So we can swap out the V for I times R. So it's going to be I times R, which is that one. And there's another one which, for some bizarre reason, is not given in the equation sheet, V squared over R. I don't know why. You probably won't have to use it. This one here, you're going to link mainly to your power lines. So power lines in the national grid. And again, using transformers, you have high voltage going up to really high voltage and really low current. If this I value is lower, Then because of the resistance in the wire, we'll come on to that in a second, the power losses are low. Just be careful, these equations, let me just switch to this colour here, these equations here, so these are my power equations. Again, I don't know why I don't have to use that one. These power equations, the language is tricky. It could be power generated or power lost or power developed. Doesn't matter. Whatever the adjective or whatever the verb is, whatever it is, power is electrical power. So it's this one. You may have to use this one as well. Just be aware that it exists. That's sort of the classic power equation that covers everything. But these are the circuit specific ones. If I know the current and the voltage, but let's just use one as a quick example. If I know the current 1.5 and the voltage 6 volts, then I know that the power is going to be V times I, which is 6 times 1.5, which is going to be 9 watts. Okay, I can do the same over here. This would be 13.5 watts. This would be 3 volt, 4.5 watts. So it's just, if we know the values for the resistance and the current and the voltage, then we can work out the power. That's all that's saying. Right, let's quickly cover a couple of required practicals. Just move this out of the way. Let's get another bit of paper. Okay, now, confession time. I made up some required practical simulation, and I forgot to include the variable resistor. I don't care. Okay, there are various ways to do it. Let's discuss the first required practical, which is resistance of a wire. Okay, resistance of a wire, and it's essentially it's going to be a power supply, like so, and we have some kind of an ammeter in the circuit, and that's going to be connected to a wire. But let's just pause for a second and let's have something over this side, like so. Now we fix one end of this to the start of a wire, and the other end we move. So this is fixed, this is movable. I've just realised I can't spell movable. I think is this. I think it is. And this wire here, we're going to have straight, but we're going to attach it or have it next to a meter stick, like so. And then we're going to measure the potential difference there. Now, that's the simple version. That's the way I used it in school. Please be aware that sometimes there might be over here, there might be a variable resistor. So there might be something over here, the purpose of which is to reduce the current. Because this thing, if the resistance is very small at short distances, the current in the circuit can be quite big. It might melt the wire. I'm sure you may have seen 1,000 Scotch marks on a meter stick if you have this set up in school. Now, a variable resistor can go in there. That just reduces the current to make it safer to handle. I don't really care. This works and works really well. So we're going to take this movable contact and we touch the wire at various lengths that we know, preferably every 10 centimeters, and we'll note down the current in the circuit and the potential difference across the wire for every length. And what you find is, let me just go to my computer here. Yes, there we go. And what you find is that you have a nice set of results. So this is a set of results that I found in a class years ago, and I think it's pre-lockdown actually. And we have the groups. We have group 1 to group 8. So we have 8 different groups, and this is their individual averages. So they did this 3 times. They took an average of the voltages and the currents for every length, and they produced the average resistance. Remember, resistance is voltage divided by current. And then we took a class average. So this would be the class average. This would be the length. So we have length against class average resistance for each length. And what we produced was a really nice graph of resistance against length. And that's pretty good actually. So for every length we have an almost a straight line that goes through the origin. So we call that directly proportional, which essentially means if I go from 10 centimeters up to 20, if I double the length of the wire, essentially I'm going to be doubling the resistance. If I go from 10 centimeters up to 50, then I'm going 5 times bigger length, 5 times longer length. I would expect the resistance to be 5 times greater. Okay, so that's quite a nice result, and that's the resistance of a wire experiment. Now, hang on, let me just go back to my studio. Okay, I think I need to check this one in the playback because I pressed 2. Let me just go to let's press 2 again. Yeah, it's fine. I think I might edit this afterwards and I might leave it in for amateur value. Because I pressed 2 there on the Excel, I think the studio software recognizes it as a 2 and went back to the visualizer. If I go to a 3, by the way, I'm on camera. If I go to a 4, I'm on the browser. If I go to a 2, I'm back on the visualizer. I think I got away with it. Now, let's do the last required practical, which is an odd one. We're looking at the current and the voltage or potential difference, or the IV of different resistors. Okay, so we call the IV characteristics. Okay, I'm up to the 40-minute mark, guys. I don't want to go too much longer. I want to stop this pretty soon. So let's finish on this. And I want to show you a little simulation, which I did way back in the day. So let's go to number 6, which is there. And let me go to the actual software. Don't press any numbers because it will jump back. So here we've got a circuit. Now the circuit here again omits a variable resistor. Bit of a bad habit of mine. So we've got a power supply which I've designed to go from 0 up to 12. We've got space for a component, and we have a voltmeter and an ammeter in the circuit. Now the variable resistor would be, okay, let's have a fixed power supply and let's alter the voltage or alter the current using a variable resistor. It doesn't really matter because we're going to see the same results. So we're going to use 4 different components, and here are the components. So now for each one we're going to draw a graph. So let's choose the 100 ohm resistor there, and then we just cycle through. We increase the voltage to 2, 4, 6, 8, 10 and 12. As the voltage increases, so too does the current, and I'm plotting the values on the graph on the right. I turn off the voltage, I swap the poles around on the supply, which means that the current is moving in the opposite direction. Increase the voltage, we get negative value. Now negative just means the current is going the other way. Up to 12, turn it off, and then we have all these points. We're going to draw a line through them, and then we're going to remove the points, and we have this. Now this is something you might recognize in your revision guides. This is something that you will definitely face in the exam if this question comes up. This is what's called an ohmic resistor, where if you double the voltage, the current's doubled. If you triple the voltage, the current is tripled. It follows a nice straight line through the origin, a bit like the graph of the results for the pupils. If we swap this out, now if we have a bigger resistor, then what's happening is for the same increase in voltage, we have less current. So our gradient is, turn it off, swap the poles, go in reverse. Our gradient is going to be less, or sorry, it'll be a smaller gradient, because for every change in voltage, I've got less, or the current will be less, because it's a bigger resistance, it'll be a smaller current. We draw the line, but again it's a straight line through the origin, but now it's a shallower gradient, it's not as steep, which means it's going to be ohmic, but it's going to be smaller, a lower gradient. bigger resistance. If we do this now for the lamp or the bulb, click it, same setup, but now we're going to increase the voltage, something happens. As we go higher voltages, the current increases at a lower rate. It still increases, but it doesn't increase as much. Turn off, do it in reverse, we have the same pattern mirrored on the other side. Turn off, we draw a line. And what's happening here is, if we think before about the resistors, the 100 ohm resistor was quite steep, the 200 was shallower or less steep, so we had a difference in gradients between two different components. Here we've got a change in gradient in the same components. It starts off steep and goes shallow, which means the resistance starts off low and increases to go higher. Just like I showed you the 100 to 200 ohms, steep to shallow, in the bulb itself, with the higher voltages, the current goes, the resistance goes steep to shallow, which means that we are increasing our resistance. And what's happening is, as the temperature increases, because the bulb is getting brighter, because you get more voltage and more current, as the temperature increases, so too does the resistance. And the reverse happens as well, and going the opposite way. Last one is the diode. It's a little bit of a dodgy one. Now here I've got it, if we use anything above 2 volts, it'll blow up. So we change it for a smaller power supply from 0 to 1.2 instead of 0 to 12. And we increase the voltage, and we have, we get nothing, 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 value, value, value. So for some reason it's not 0 and then it jumps up. Turn it off, swap the poles, increase the voltage, and it's not quite 0. It's a little tiny value. Okay, so let me explain the shape of this one. Let's draw the line and let's remove the points. So this is the diodes, and diodes work in one direction, but even then they only work after a certain voltage across it is achieved, around about 0.7. There's many reasons for it. We do not have the time nor the energy to go into them. So diodes work in one direction. In reverse, they block the current. In reality, there's a slight what's called a leakage current, which sounds a lot worse than it is. It just means we don't exactly get 0, it's essentially 0 amps. Okay, it blocks the current, but in reality there's a little tiny amount that's leaking through. So diodes essentially are one-way roads. Okay, if you think about our model for lorries and supermarkets, the diode is a one-way road. Okay, if you try to push the lorries down a particular road, the opposite way, they will be blocked. So that's the diode. So you have to know these values. Let me just go back to my software, and then let's go back to this. So a couple of things I said there. We have ohmic, and this is for a resistor. We've got, let me do it in different colors. We've got this, and then we've got this one here. This would be high resistance, this would be low resistance, and the axes themselves is voltage, potential difference, and current. Now it's ohmic because it is the same resistance for every voltage. It doesn't matter how big the voltage is, the current is proportional, so it's the same resistance. V over I gives us the same value no matter what we choose. Non-ohmic, okay, and that could be a lamp, have the same axes, voltage and current, but now we've got some kind of a S shape, and essentially we've got a steep gradient, so it's going to be low resistance here, and as we go up, the gradient becomes shallower, a bit like the blue line, so this would be high resistance. And that happens because as you go from here to here, the temperature increases. And this pink pen is really absorbent in the paper, so I need to write bigger than this. So that's called non-ohmic. That's a shape that you'll find. Last thing, I want to show you a really cool little simulation to explain a question that has come up quite a few times. So let me just get a bit of paper and then we'll draw it out first. Then I'll show you the simulation and then we are done. So 50 minutes, yeah. So let's swap around. Let's have this paper here. Okay, that'll do just now. So resistors in series. As I just said that, my phone thought I said "Hey Siri." That's what the Beat Boys, if you heard it. R1, R2, R3. To work out the total resistance of these three resistors, it's simply just R1 plus R2 plus R3. And if I had a fourth one, or a fifth one, plus anything. We call this RT for R total. Now in parallel, it's a little bit messier. So we could have three resistors, one in the middle, one up here, and one down here. And this is again called R1, R2, R3. Now here, I'm afraid, it's not as simple as this. Okay, and I want to show you in the simulation what I'm talking about. So let's go to the browser, and then we go to the browser itself, and then I want to show you this. So here's a circuit, and I've got I think it's a 10, just check the voltage. Yep, 10 volt DC, so direct current, so the current goes in one direction, and the yellow dots are the charges, so they're in the circuit already, they're all throughout the circuit, but I've disconnected the circuits. I've got 10 volt supply. Let's connect up the 100 ohm resistor. And so Ohm's law says 10 divided by 100 gives me 0.1 amps, or 100 milliamps, and the yellow charges move. They move through the circuit. Let's turn this off. Let's go to the 400. 100 divided by 400 is 0.25. So hang on. 10 divided by 400 is 0.025, so 25 milliamps, and fewer lorries per second. You can see here that the yellow dots are going slower. Turn this one off. 10 divided by 500 is going to be 0. If I'll just press a number to see them. Yep, 0.02 amps. So that's going to be 20 milliamps. Again, slower still. So each resistor will determine the current that comes out the cell or the battery. Now, here's the tricky thing. What happens if I put two together? Let's turn on the 100 and also the 400s. Now you might think it's going to be somewhere between 100 milliamps and 25 milliamps, but if you throw the switch, we end up with 125. How is that possible? So let's deal with it in terms of lorries again. The lorries all come out of the battery with 10 volts. The lorries that arrive here, 10 volts. The lorries that arrive here are also 10 volts. And they must leave this branch with 0 and 0 and go back in empty. So between the top and the bottom, down the separate branches, 10 volts is lost. So this resistor here demands 100 milliamps. This resistor here demands 25 milliamps. Each of them demands what they want, so what must be provided for them is 125. If I throw now the last switch, remember, was demanding 20 milliamps. So if I press this switch, then this will be demanding its own 20 milliamps. Add that to the beginning, and this should be 145 milliamps. So the more resistors you add to the circuit, and they all demand their own current, the more demand there is on the current from the battery. If I added a fourth resistor, say it was 1,000 ohms, then that would be 0.01 amp, This would go up to 155 milliamps because it needs its own current. The battery has to supply it. Now, what does that mean? Okay, let's go back to the software. We're almost done. And so, if this resistor demands 2 amps, so let's say this one demands, I don't know the values. Oh, I should have stuck to my colour scheme. We're in blue. 2 amps of this one. 3 amps. And 4 amps. Each of these demands the amps that they need. How much do I have to provide? The way I think about it is as follows. Say these are 3 people, and I want to give this one person 2 sweets. This person I want to give them 3 sweets. This person I want to give them 4 sweets. How many sweets do I have to begin with to provide for the 3 people? 2 plus 3 plus 4 makes 9. Now, how do I calculate using these values for R1, R2, R3 to get 9 amps? I'm going to give you the equation. You don't have to know it, but you have to understand why it is 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And this question has come up a couple of times, and what you're saying is each individual component resistance demands the current that it needs based on the potential difference across it and the ohms or the resistance value itself. And so each individual resistance demands its own current. That has to be provided by 9 ohms by the current from the battery. If it's 2 and 3 and 4 amps, I've got to have 9 to begin with. When we do this calculation, then it turns out that this total resistance for all 3 values is actually much lower than the smallest value. And if we do the equivalent resistance for the whole circuit, then it'll come out with a value that gives us the 9 amps. Now that's tricky. I want you to go and research it. But if I want to just give you a quick example, because even though you don't have to use this equation, to see an example working out, it's quite beneficial to see where the numbers come from. So let's finish. Let's do this one really quickly. Let's do 3 resistors, and let's do 2 ohms. Let's do 3 ohms, and let's do 4 ohms, and let's have and let's have 10 volts. So my question would be, what is the current that must leave here? And I want to figure that out by reducing this down to an equivalent circuit, which is 10 volts and some total resistance. So let's tackle this one then. I'll use blue because my black's running out. So we have 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3. If we find the lowest common denominator for all 3 of these, then that's going to be 12. So this would be 6 over 12, this would be 4 over 12, and this will be 3 over 12. That together is equal to 13 over 12. As I quickly check my maths, yes, I think it is. But remember, that is 1 over RT. To get RT, we just swap both over. So we have RT over 1 is just RT is equal to 12 over 13. And let me just get the numbers. So let's just do 12 divided by 13. So it's 0.9, call it 0.92. Now, 0.92 ohms is the equivalent resistance. So 10 volts, as we do the calc, 10 volts divided by, 0.92 ohms gives us 10.9 amps. That's what I've got to have coming out the battery. And then individually, remember, it's going to be 10 divided by 2, which is going to be 5 amps. 10 divided by 4 is 2.5 amps. And 10 divided by 3, again, I should have thought these numbers better beforehand. It's going to be 3.3. If I add these together, so 5 plus 3.3, there we go. So we get our 10.83 back. So this plus this plus this, because they each demand separately these currents, I've got to provide 10.9 amps. And I can calculate that 10.9 amps by doing total resistance, which is less than the smallest value. You don't have to do the calculation, but you have to know why the current is what it is and why the total resistance is less than the individual values. Okay, that's hard. Good luck. And I'll do a little revision session for the rest of the P1 paper. Bye.